Very good morning. Yeah, I have started the recording. Okay. so so any questions in the last class related to? Hmm? Hmm? Yeah. So can you see the presentation, slide presentation? Hello?
Yes, sir, it is visible.
Yes, yeah, yeah. Okay, good. So so in the last class we have started the design of processor. It's nothing but knowing about how to design a data path. It's nothing but the different components or entities that are present in a processor to help or to perform the actual operations. It's known to be data path or the components of a data path. And then after that, so how to control this data path or how to control these components so that the instructions will be executed properly. So the designing a processor is nothing but just to knowing about the designing a data and its controller for execution of a set of instructions of a specific instruction set. So in that, actually, we just very briefly discussed about very overview of what is meant by data path, what are the control signals, and all very briefly at a very like gross, superficially we discussed, and after that we discussed about like various data path components that are involved in execution of various or in implementation of various instructions that are required. And we had discussed about like for a particular set of instructions, like for a particular group of instructions, like R format instructions, like memory reference instructions, or instructions, or like conditional instructions. So in these various types of instructions, what are the different data paths that are involved? So those things we have discussed in the last class, like one after another kind of a thing. Like specifically for R type instructions, what will be the data path, how it looks like. In case of load and store instructions, how the data path look like. In case of branch instructions, how the data path look like. So likewise, we have just gone through that. Like for example, this is for branch instructions, and likewise, these are the components that are required for load and store in addition to the R type. So likewise, these are the various things we have discussed in the last class. And now, but when you are designing a processor, means the processor should implement all the instructions, not just R type or load and store or branch. All of them implemented by the same the data path. So it's nothing but whatever we have discussed, whatever the individual components are in, should be integrated together so that a single data path that should work or that should implement that can able to execute the all the types of instructions in a fair way and all. So that's what we are doing over here. And so now in this today we'll try at how to like compose all the different data path elements, different data path components to create a single data path with which you can able to execute all the instructions of a particular instruction set architecture and all. And so now if you look at here, suppose this particular data path, this is here, sorry, the first initial data path, which is common for all the instructions, that was not here just for the sake of space constraint. There is nothing but instruction memory, PC, and all that was not shown here. And the remaining data path that is for can be used, can be both R type and as well as the memory reference instructions, load and store instructions. because all these instructions you use the register file, then the ALU unit, and then the data memory. And anyway, you have instruction memory is also required to fetch the instruction and all. So yeah, these things we come across. This is just a merger of both R type and the load and store type instruction, because for load and store type instruction, you use this sign extension is required, where the offset will be like of 16 bits to be transformed to 32. It's equivalent 32 bits, and then the corresponding multiplexer here, and then in only ALU and register files are used. Outcome of ALU will be bring back to the register file for writing into. So that way, all these components that are involved in that can be used for both either R type or load and store data type data path. This is the combined data path which can able to execute both R type instructions as well as load and store instructions. Whereas this one is nothing but here you can see here, which we have already seen that this can execute both R type and load and store. And now this figure is a complete data path is nothing but just including the instruction memory PC. Here we are also includes one more other type of instructions, known to be branch type instructions, where here the condition, the statement or instruction contains some condition has to be checked. Based on the condition, the next instruction to be executed depends upon the condition validated by the instruction and all. Also takes care of the branch instructions in addition to R format and load and store instructions and all. So this particular circuitry, whatever here, like here this particular again add circuitry, and then this one's for computing the branch address and all. And anyway, this ALU is used for computing the checking the condition and all. And so this is the complete data path which you can able to execute R type instructions and load and store instructions, that is a memory access instructions, and the branch instructions as well. And here this is the data path, and then to operate this data path successfully for execution of instructions and all, so we need to tweak the controls so that the space will be implemented successfully and all. And in the next part, we'll try to see that how do we design the controller, or how do we generate these control signals with respect to a specific, with respect to each of the given instruction. And if you look at here, the control signals involved are for there is one control signal which used to be like a register write. It means that whenever high, right? And here again, these are the multiplexers here as a signals to be fed to a single input. And this among these multiple signals, any time only one signal has to be driven, one signal has to be input and all. And so for that purpose, we use the multiplexers, where here you can see in case of ALU, one multiplex between the two inputs, right? One is from the immediate addressing, and other one is this for register address. So in this case, out of these two, one has to be given as the input and all. So therefore, multiplexer is required. Here also, in case of to be fetched, that depends upon the branch. In case of branching, again, there will be a multiplexer. It has to be pick up whether the next address will be the branch address or the next instruction address. So that depending upon the condition of the whether the condition is successful or not. Okay, here also we need to have multiplexer. Here also you can see here there is one more multiplexer here, where here we are writing back into the register. So when you're writing back into the register, there are two possibilities in the instruction set. You are writing back once when you are reading a data, when you are fetching a data from a memory. That is, in case of load instruction, you fetch data or you fetch from the memory and then write into the register file. And another possibility of writing back will be when you're performing arithmetic operations like R format instructions, the end result will be again put back or again bring again will be right into the register. So for there are two possibilities that you can say that types of instructions. So therefore here we have again a multiplexer is required to use one of them, like which one has to be done, which one has to be picked up. That will be driven by the control signal by the given as input to the multiplexer. Similarly for a memory also. So when to read or when to write, for correspondingly we use the like memory write and memory read control signals and all, right? And another thing is that here we have ALU. You know that ALU is a multifunctional unit, so which we have already seen that it is capable of performing various arithmetic and logical operations. And then depending on the requirement, we need to use ALU sometimes maybe for adder, sometimes maybe for ORing, sometimes maybe for unding, sometimes for checking the condition like less than or whatever. So that way here the ALU has to be controlled. So therefore we need to have some control signals to the ALU. So with that the ALU will be correctly function, like the appropriate function has to be implemented by the ALU and all. So these are the various control signals. And now we'll see that actually how do we design a controller, or how do we generate these control signals for the different instructions. So before going to that details of that, you have seen, if you look at here, there are about there are about 1, 2, 3, 4, 5, 6, and ALU has again 4, and yeah, these are the various, and here there is one more multiplex also will be there that we'll introduce here, because if you look at here, when you're writing the data into the register file, along with the data, you also need to specify the address also. You need to specify the address also, address where the content has to be written into the register file. And this address is not unique. This address will be varying. In case of R format instructions, the address of address registered to be written will be different. And in case of load instructions, the address to be written will be different and all. So therefore, we need to pick up the right one for a given instruction, whether it's a load instruction or R type instruction and all. At that time, again, the address to be feeded here, address to be here given here, that also will be passed through a multiplexer, because there are two possibilities. So therefore, we have one more multiplexer is required. So what I mean to say is that for all these control signals has to be properly activated based on the instruction. So for that, we'll see that actually, and you have seen that there are about 10 or 12 control lines are there. Control paths, control lines are there, and then for every instruction, we need that actually how this, which of the control lines to be activated, which of the control lines to be not activated, and all. And so the designing a circuitry, designing a controller is nothing but we need to design a combination circuit. We have seen that, like for example, we have seen a very simple one. In case of adder circuit, we have seen that 1-bit adder. So what are the inputs for the 1-bit adder? We have the two inputs A and B as the inputs, and output will be like sum and carry out. These are the outputs. And for that, we have seen that there is a carry in also will be there. So therefore, for designing the adder, 1-bit adder, you have three inputs. One is the 2 bits, like input bits from the, and then another outputs, and then for the output will be the two possible outputs. One is the sum and other one is the carry out. And for that we have designed a circuit, like we have a truth table is nothing but what are the various possible inputs. Since there are 3 inputs, we have 8 possibilities are there, and they have corresponding outputs are there. Sum will be 1, and when the carry out will be 1. So based on that, you can able to design the circuitry. So that itself is that's a way the controller will be designed. So in case of adder, we see that there are 8 combinations, and then we have the corresponding sum and the corresponding carry out output will be there. And then you can able to design a combination circuit using a principle of either product of sums or sum of products, and by optimizing that, you can able to do that. So the same way here also, we have to design a controller that here for the controller, the output of a controller will be all these signals. The output of a controller will be like all these things, whatever the signals we are passing to the multiplexers, memory, register files, and ALU. So all these are happens to be your output. And what is the input? So the input will be based on your instruction type or based on your instruction. What is the instruction here? The instruction is specified by the opcode, right? So the opcode will specify that what is the instruction, what is the type of instruction and all. And again, within the format, within the specific type, there are some categories will be there. For example, in case of R format instruction, the opcode will be 000, like the most significant bits of that particular instruction, like 26 to 31. Those bits are all of them are 1. But in case of R format instruction that perform varieties of the multiple varieties of functions, it can do the add, it can able to also need to perform subtraction, it also need to perform some logical and logical or. So all these things can be discriminated by using a function field which is at the lower significant 6 bits and all. So that way, the instruction, the nature of the instruction or a type of the instruction or the task that need to be performed by the instruction will be understood or will be come to know by using the opcode field and the function field and all. So now if we have to design a circuit, means actually here the circuit has to be designed such that the details of instruction, or you can say that the nature of instruction details which are available from the instruction word from the specific bits, whatever as I mentioned, like the most significant 6 bits and the least significant 6 bits. So that means there are total 12 bits. So with that we'll come to know about the type of instruction or what is the operation that need to be performed and so on. So that will be known by using those 12 bits. And what is the desired output? The output will be that. So for that particular specific instruction, what are the control lines to be activated? Right. So there are total 12 control lines are there, 12 or 11, whatever. And these control lines to be, some has to be activated, some has to be deactivated and all. So now we need to derive the circuit. We need to derive it's a kind of set of inputs and we have set of outputs. And it's nothing but a kind of a truth table with the multiple inputs, like we have 12 inputs and 12 outputs and all. And then we need to design a circuit for optimizing the components that are involved to perform this one, input to the output. So as mentioned, I try to see that in case of adder, how we have done that. In the similar way here also you can able to do that, but here it's most complex one, more complex, because they have 12 input lines are there, the 12 outputs and all. You can see that what are the possible inputs. 12 means 2 for 12 possibilities will be there, like here also. So out of that, all may not be used all the time. So therefore, by using some optimization techniques and all, able to reduce you can able to optimize the circuitry also. And one way to, instead of designing a complex controller in a monolithic way, we can able to reduce the complexity by making the design by designing the controller at a multiple levels and all. So for that purpose here, what we are doing is that instead of performing the controller control lines, based on that the ALU functionality will be carried out. So first we'll design a small controller which is just mentioned, which is to be controlled just the ALU, which used to control the ALU. And then the other control signals will be generated from the main controller. That means that we have a main controller, and the main controller will provide some input to the ALU, and then the ALU controller will take that input and make use of some other bits, and it will generate the ALU control line separately, and the other control lines will be driven from directly the main controller and all. So we'll see that. Otherwise, actually, if you want, you can able to design a single circuit also. It's not a problem, but it will be more complex and all. So to reduce, and not only that, the delay that is involved also will be increased. So to minimize that, to reduce that, optimize that, you can able to design a complex controller instead of in a monolithic way. You can able to design at different modules, different controllers, subcontrollers, or controllers at different levels, and all of them put together will serve the purpose of the overall controller for controlling the given data path and all. So for that purpose, first we'll try to see that how the ALU will be controlled. Then afterwards, this ALU controller will be act as a submodule or like the control, a smaller controller, which used to be controlled by the main controller and all. So we'll see that how do we can do that. And as we have seen that already when you're discussing about ALU, so this is the ALU control lines for performing various operations and all, right? And we have seen that all these things. And this ALU will be used by all the instructions like load and store also will be used ALU, branch instructions also will be used ALU, and R type all instructions also will be used by the ALU and all. And whereas in case of load, store, and branch instructions, like there won't be any function field and all. In case of load, store, and branch instructions to perform these two types of instructions, there is no function field because in both the cases, load, store, and branch instructions, both will fall under the immediate format. Immediate form. That means the lower 16 bits, the 16 bits of the lower significant side, so they indicate the offset and all. So with that offset will be used for address calculation. Whereas R-type format, the lower 6 bits, that is the 6 bits at the LSB side, so they are used to indicate the function field. That means what specific function has to be carried out by the ALU and all. Whereas the load, store, and branch and all, so that function field will not be there at all. So that is not at all considered as a function field. So, but the load and store and branch instructions also will use the ALU, will need the ALU for performing. For in case of load store, the ALU will be performed, will be used for addition purpose because the address will be calculated, base address plus offset. Whereas in case of branch address, the ALU will be used for subtraction purpose because in case of branch address, we had to check for branch of equality and all. So for that, we perform the subtraction. Based on that, we can generate that whether it's equal or not. So whereas R-type, it performs all logical and arithmetic instructions and all. So for this, we need to design, first of all, a controller for this particular, for controlling the ALU for all these instructions and all. So for that, what we can do is that actually if you look at here, so these are the different types of instructions, right? Various formats like load and store, and this is a branch and equal. And these are the R-type instructions. Like I have not mentioned here, we have several R-type instructions which vary based on the type of operation to be performed, whether the subtract or and so on like this. And here and then this is the function field, and you can see that in case of R-type instructions, we have a various function fields will be there. It means that the lower significant 6 bits and all. So they indicate that they indicate that what is the type of operation to be performed. If it is a 32, then the operation to be performed is add. If it is something like 34, the operation to be performed is subtract. So likewise, these function bits, so that will indicate that what operation to be performed in case of R-type instruction. Whereas in case of load stores, like the other instructions like memory access or the branch instructions and all, so there is no function field at all. So in that case, we need not bother about the function field. So therefore, we can simply replace with the don't case, because whatever it may be, we don't consider this at all. So we can just represent by using don't case, because the representation of don't case will be useful for minimizing or for optimizing the designing the gates and the circuitry and all. Right, and these are the and here these are the different and here at a broader level, the instructions are varied based on these types: R type, and then the memory type, and then the branch or control instructions and all. So what we can do is that even though the load, store, and load, store, and then branch instructions and all, so even though they don't have a function field, but still they need the ALU to perform something. So for that purpose, and here that will be known only from the opcode and all. So therefore, the ALU controller requires the inputs from the function field, because the R-type instruction will provide that the opcode will be like all zeros, but the variation of operations depends upon the function field. But in case of load, store, and branch and equal and all, the function field is of no use at all. There is no function field at all. So therefore, to perform the ALU operation properly, so first of all, by using opcode, we need to decide that what is the type of instruction, whether it is a memory reference or whether it's a branch instruction or whether it's R-type instruction. So that information will be provided to the ALU circuitry so that the ALU will generate appropriate control signals and all. So what I mean to say is that the actual ALU controller requires the inputs like from the opcode as well as from the function field also. Again, from the opcode, we don't require much information at all. We require just information about what is the type of information. It is what is the type of the instruction, whether it is a memory reference or whether they are the control instructions or whether they are the like simple R type instruction like arithmetic and logic instructions and all. So therefore, you can simplify this ALU controller like instead of using all the opcode bits and all. So from the opcode, somehow we can able to generate two control signals which used to indicate the type of instruction because there are three types here in this case. So these three types can be represented or can be indicated by using the two bits or the two control lines like the 00 something like that 0110. And then this information indicates that what is the type of instruction. And along with this information, if we can able to feed these function fields to the ALU controller as input, and then with that we can able to generate, yeah, this is the desired output in case of ALU controller. So this is the desired, these are the control lines, these are the control signals that are required in case of add, in case of subtract and all these things. We are seeing that the ALU requires the 4 control signals. And this is the output for the ALU controller. So what is the input that is required? Function field. And in addition to that, we also need the type of instruction, right? A broader type, broader category of instruction, memory reference or branch or this one. So the way it will be performed will be here. This type of instruction will be generated by the main controller. It just gives you the 2 signals and all. And along with these 2 signals, and these functional bits also will be used as input to the ALU controller. And with that, the ALU control will generate the corresponding control signals and all. So if you look at here, for designing the ALU controller, so the input will be something like this. You can see the above figure is same as the previous one only, just the same as the previous one. And here the below one is that nothing but the truth table that is required for generating the ALU controller. The truth table means what I mean to say is that what are the inputs and what are the outputs and all. Here these are the 8 inputs. You can see here ALU output means there are 2 outputs as I mentioned. ALU output means ALU operation, sorry. So this is just to indicate that from the opcode we can able to generate that what is the type of instruction, whether it is a load store or whether it's a branch instruction or whether it's a R format instruction. So that is indicated by the 2 bits and all. And then the function field is indicated by 6 bits. Function field is indicated by 6 bits and all. So the combination of these 2 bits and 6 bits that forms the input to the ALU controller. And the desired output of ALU controller will be these 4 bits and all. So that way we know that actually the input, there are 8 inputs and the 4 outputs. And these 8 inputs has different combinations. And here again I introduced a don't case and all. Don't case indicate that actually here that particular bit has a no value, either 0 or 1, it doesn't matter. So because the function fields for this load and store, as I mentioned, that it's no significance at all. Similarly for branch instruction also, you can see that there is no significance at all. And similarly, if you observe these function bits also for this particular instruction, for this particular operations, if you look at here, out of the 6 bits, the last 2 significant, the 2 most significant bits, they are common across all of them. That means there is no variation at all. So therefore, you can also represent with all of them with the don't case. And because we are keeping don't case because that simplifies the circuit design and all. So that way. And similarly here also, if you look at here in this ALU operation, that means ALU derives the 2 signals. Out of these 2 signals, we have only the 3 are required. That is for load and store, that is for memory reference one type, and branch is another type, and R format. And here there is no like 1 is not there at all. So therefore here, since 1 is not there, so therefore there is no problem in representing this zeros 0 1 or 1 0 as don't care 1 and 1 don't care and all. So that way you can able to represent the truth table for ALU controller. And once we have the truth table, because these are the 8 inputs here, the 8 columns, the first 8 columns are the inputs, and here this particular the 4-bit operation, that is the output and all. So there are 8 inputs and 4 outputs. So with this you can able to design the ALU controller and all, because there are lots of don't case are there. So therefore you can able to simplify the circuitry very effectively and all. So this way the ALU controller will be generated, right? And once the ALU controller is implemented or is designed, then this ALU controller will be a part of the main controller. A part of the main controller, we'll see that what it is. And otherwise, if you directly go, it will be easier for you. And the main controller means, yeah, somewhere here. No. Let me just show the, yeah, this is a kind of controller. You can see that this is your main controller, right? That means controls the main controller. For this, the input will be like, you can see that the most 6 significant bits of an instruction, that is the opcode, that will be your input. And from this input, it generates all these control signals. And in these control signals, it generates the ALU op. That means it just specifies the ALU operation as 2 bits, And this is your ALU controller. And this is your main controller. This is the subcontroller, which used to be just look after the controlling the ALU circuitry. That's all. And for this ALU controller, so the one input is coming from the main controller as the 2 bits that indicate by this R type or branch or load store and all. And it also make use of the functional bits. So where the functional bits are available here, this is your instruction word available from here. In that, the lowermost 6 bits, like 0 to 5 bits of this instruction word, contains the functional bits. So this is also input. So for this ALU controller, we have 2 inputs, the 6 bits as well as the 2 bits from the generated from the main controller. And with these inputs, 8 inputs, it will generate the 4-bit output. So this 4-bit output will control the ALU and all. And in addition to that, the main controller will be used to generate other signals, like the signals for these multiplexers. You can see there are 4 multiplexers over here and all, right? And signals to the controlling the memory, data memory, and signals to control the register files. So there are, in addition to these, there are 7 other additional control lines, control signals that will be generated by the main controller and all. So here, why we have splitted these two is that otherwise, actually, if you also merge with that, then the output will be like there are 12 outputs and the input will be 12 inputs. So that becomes the circuitry becomes more complex for designing as well as for implementation also. For that reason here, we split the controller into the 2 parts. One is the ALU controller, other one is the main controller and all. And so, yeah. Now with this background, actually, if you look at here, with this background, if you look at, these are the various control signals, and here the purpose of the control, that means where the control signal will be on and where the control signal will be off. So that is given in this particular description and all. That means, for example, if you look at the register destination, that means if we want to write something into the register, so that will happen in 2 cases. One is the load and other one is the R format instruction, right? In case of R format, in case of like there are load and R format. So that means out of these 2, one has to be chosen, that depending upon the instruction. If it is R format, it has to be chosen that the 15 to 11 bits of the instruction has to be given, has to be treated as the address. If it is a load instruction, then the 16 to 20 bits are treated as a destination address. Because in case of load instruction, if you remember, there will be offset of 16 bits. 0 to 15 will be your offset, and afterwards the registers will start. In case of load, there will be 2 registers will be there. One register meant for the base address, other register meant for the keeping the data into that. So therefore, the 20 to 16 bits indicate the destination registration address, register address in case of load. Whereas in case of R format instruction, there are 3 registers operands will be there. So therefore, 11 to 15 bits indicate the destination register address where the result of the arithmetic result will be stored there and all. So these 2, out of these 2 addresses, one has to be chosen while writing the data into the register file. So that choosing this one is controlled by the controller. The controller will pass the signal either 0 or 1. If it is a 0, something will be selected. If it is a 1, the other one will be selected and all. So that way, deasserted and asserted. Asserted means 1, deasserted means 0. So that way, the other control signals also. The explanation is given. It's very straightforward. Or in case of multiplexers, out of 2 inputs, one has to be chosen. And likewise, in case of read and write memories also, Whenever it's 1, then the particular thing will be activated. Yeah, right. So yeah, this is the like the overall main controller output will be like this. In case of different, in case of main controller, the input is only 6 bits, right? The input is only 6 bits. You can see the 6 bits. 6 bits is nothing but opcode, and from the opcode you need to generate these 9 outputs and all. You need to generate how many? Yeah, 9 outputs. Out of the 9 outputs, 2 outputs will go for as input to the ALU controller, ALU op1, ALU op2, and the remaining are for the control signals for the other multiplexers or like data memory or register file and all. There are 4 multiplexers are there, and for data memory 2 inputs are required. For register we have 1 input, register file 1 input. So total 7 single bit control lines, and these 2 control lines will be part of the ALU controller circuit and all. So this will be the output from the output signals that need to be generated from the main controller and all. And for that, the input will be the opcode. So the same thing here, the same table, it is represented in other way. If you look at here, these are the outputs, like these are the 9 outputs here mentioned here in the below table: register, destination, ALU source, and so on. These are the 9 inputs and 9 outputs, like, and these are the inputs. Like input is nothing but opcode 0 to 0 to 5, that 6 bits of opcode and all. So here you have to treat this the truth table as like this way, like it's not like horizontally, it's like vertically it was there. So yeah, these are the inputs. The first 6 rows are the inputs, and the bottom 9 rows are the corresponding outputs and all. So if you can able to design this, this is the main controller design, and the one whatever we mentioned earlier, that is the design for the ALU controller and all, right? So here also you can see that some places we introduced don't cares and all. It means that in those cases it's not valid. That means the bit is the value of the signal is like it's of either 0 or 1. It's immaterial and all. So this is the way you can able to design the control circuitry and all. And yeah, here, while design a control circuitry, here we had to see that actually which has to be activated, not activated and all. So that is illustrated over here. You can see here there are 3 types of broader instructions, the R type, load, branch and all. And if you look at these instruction formats here, you can see that in case of load, store and branch and all, so these 16 bits are considered for sign extension. And then afterwards, as I mentioned, that in case of write back or writing the contents into the register file, so we need to see that these two, like in case of R format instructions, as I mentioned, that this is your destination address, where the bits are like 11 to 15, not 11, yeah, 11 to 15, yeah, 5 bits, yeah, right. So this 5-bit field indicate the destination register where the result has to be stored over here. And in case of load instruction, this is the destination register, that is 16 to 20 bits that indicate the destination register address and all. Out of these, one has to be selected using appropriate multiplexer and all. And if you look at here, this particular field 21 to 25, all the time these are the source register. That means that by default it will go to the one input of the ALU and all. One input of the ALU, whatever it may be, whether it may be R type instruction, load or branch, whatever and all. So all these, the 21 to 25, like blindly it will go as one of the input of the ALU and all. So the other input will be varied. The other input will be varied, except only for the load, only for the load and store, except load and store. So the other input will be varied. In case of for load for R type instruction, this will be the second input to the ALU, and even for a branch instruction also, this is the second input to the ALU, right? But in case of load and store, where the second input is not from the register, the second input is from this immediate format. The second input is from the immediate format and all. So that way it varies and all. So accordingly, we need to set the control lines, which register to be selected or what can be done, whether the writing has to be done, reading has to be done. So this has to be controlled by appropriate the control lines, which is provided by the controller, whatever we have discussed. So right? And yeah, this is what we have seen here. And yeah, this is the main controller, and these are the various like output from the controller and all. And here, if you look at here, in case of the other things are fine. In case of a branch instruction, if you look at the way the controller is designed, if you see here, in case of branch instruction, here the controller, that means by looking at the opcode, the controller will know that whether it's a branch instruction or not, because the opcode for a branch is like 4 or something. So with that, it will come to know that it's a branch instruction. So then immediately this branch output, whatever the control signal, this will be on, this will be 1. And other than the branch instruction, this branch will be 0. If it is a branch instruction, then only we need to check whether the PC has to be loaded with the PC plus 4 or the branch output or the target output and all. So therefore here, when if there is a branch instruction, then this particular control line will be 1. Otherwise, for remaining all instructions, this will be 0. So whenever this is 0, it means that whenever it is 0, then in this case, this AND gate output will be 0. So it means that this acts as a like a selector control line. So where the 0 will be selected. 0 will be selected. 0 is selected means what is the 0 here? For the 0, the input given as a PC plus 4. That means the next instruction will be provided and all. The next instruction will be provided. Next instruction will be fetched and all. And whereas if AND gate output equals to 1, it means that is a branch is successful. That means the AND gate output equals to 1 means here there are 2 inputs to the multiplexer, 0 and 1. For the 0, the next instruction address is given PC plus 4. And for the 1, the input given as the branch address. Branch address means that is generated from this one, like 16-bit offset and then shifted by left because it's a word address and all, then added to the PC plus 4. So it's a PC relative address, right? But it's a branch address. So branch address will be selected if the AND gate output equals to 1. So when the AND gate output will be 1, if both are 1s, it means if the branch control line will be 1, and at the same time, the ALU result also should be positive. Sorry, not positive. The ALU output is nothing but the ALU should produce a 0. It means that here, in case of branch and equal means we are passing the 2 arguments, register arguments, and then you are checking by the ALU. If both are same, it means that ALU output will be 0. So whenever ALU output will be 0, at that time here this signal, that means ALU will send the signal as 1, as the signal as 1. So when this signal is 1 and when the branch is 1, at that time, so this multiplexer will pick up the input address from the input 1. That is nothing but branch address. In all other cases, you just pick up the next address, the PC plus 4 and all. So that way, in case of a branch address, the control line will be given by both the control line. It depends on both the branch instruction, because whenever the branch instruction is executed, at that time only we have to think of whether to branch or not. If it is any other instruction, then we need not bother about. So therefore, for all other instructions except branch, this control line will be 0. So therefore, it always pick up the PC plus 4. And whenever the branch is there, then it has to check here. This is on. This is one branch control line, and along with that, also check the condition. If both are satisfied, that means both are 1, then output will be 1, and the corresponding will be picked up. So that way, the branch instruction, the controller will be carried out. It is appropriately the branch address will be target branch address will be feed it to the PC, and the corresponding instruction will be fetched out. And yeah, and now here these are just to illustrate that once if we know the overall data path and controller. And after that, here this is just to illustrate that in case of R-type instruction, so this is your complete data. If you look at here, this is your complete data path as well as a controller. That is nothing but it's a processor, where this particular processor can execute, maybe here in this case it may execute the 10 instructions or 9 instructions, whatever, load, store, and some arithmetic instructions, and then the branch instruction and all. So that means this particular circuitry can execute all these 10 instructions. Any of the instructions out of these 10 instructions will be executed and all. And now the later one here, this is just to show that in case of R-type instruction, which part of the data path will be executed, will be like functional and all. In case of R-type instruction, we know that anyway, these first the PC and the instruction fetching and all, they are common across all instructions. And afterwards, register file. In case of R-type, it will be will pick up the we will take the inputs from the register operands. So therefore, this register file will be active. It's a part of a data path. And then anyway, ALU will be there because R-type instruction, the arithmetic or logical operation has to be done. And then, but the data memory is not there, not part of that, because we don't access the data. We don't access the data memory in case of R format instruction, because all the like operands, all the values are available in the register contents as part of register content. So therefore, there is no need to access the data memory. So therefore, if you look at here, the data memory is not highlighted and all. It means the data memory is not part of the data path in case of R format instruction, right? And similarly, you can see that since it is R format instruction, so there is no ambiguity. There is nothing. No need to compute the branch address and all. So therefore, the corresponding things also not there. Likewise, sign extension is also not required. Right? So you can see that all these things. But these multiplexers, all multiplexers are active, right? Because this multiplexer is active because we need to pick up from the whether it is from the 11 to 15 bits or from the 16 to 20 bits, right? Because both choices are appropriate with respect to the respective instructions. In case of load, store and all, the 16 to load 16 to 20 has to be taken for writing back. But whereas in case of R format instruction, only 11 to 15 bits are used. So therefore, we had to this multiplexer is required, and yeah, this is this in this multiplexer also, because there are two inputs are this is required here also required, and here is also required. So all four multiplexers are required. Are required means they should be functional, because out of these one has to be taken, one has to be passed to the next stage and all. Okay, then coming to load instruction, if you look at here, load instruction, this yeah, here in case of load instruction, like all components are active, because load instruction will make use of all the data path components, because fetching, then afterwards it make use of register file, then the ALU for address generation, then the data memory for fetching the data, and then again register file. So this all of them were active. The only thing is that the branch address, the branch related circuitry, that address computation, is not required and all. So therefore, this is not highlighted and all. So remaining all are, you can see that it is highlighted corresponding paths and all. So this is the data path for load instruction, and this is for branch unequal. So in case of branch unequal, if you see that the data path components which are active were anyway PC plus 4 or the branch address computation, these two, and ALU is required because to perform a comparison and all, and register file is required because the operands are there in the register file and all, and for branch address means the sign extension is required. Data memory is not required, and since we are not writing anything into the register, this multiplexer is also not required, right? So therefore, so the remaining or the data path corresponds to the branch unequal, right? Then yeah, so far yeah, we have so far we discussed about instructions which are load, store, and some arithmetic instructions, R format instructions, and the branch unequal, branch are not equal, whatever. And so now our earlier data path or controller, which can be used for performing execution of the instructions, whatever we mentioned. And now we'll see that suppose we want to add one more instruction, then what are the changes that need to be added, or what are the modifications that need to be incorporated into the existing data path or controller, so that the additional instruction also can be done, can be carried out on the slightly modified data path or controller. So if you look at here, in case of a jump instruction here, the format is simple, like you have opcode, right? And then followed by the opcode, you have the address. That means opcode is 6 bits and remaining entire thing is the address part of that. And we know that how to calculate the address in case of a jump. Jump means here basically it's unconditional one. There is no need to check any condition at all. So this just tries to change the control. Instead of picking up the next word in PC plus 4, it just go to the just pick up the instruction from the some other else location somewhere else. So for that we know that how to compute this address, and we have 26 bits over here. This is the word address. So to generate a byte address, so we have to shift it by 2 locations. So that's what top. So therefore, then it becomes 28 bits. We have 26 bits are here. So when the word address is converted to byte address, this becomes 28 bits, and we have 4 more bits are required. So those 4 more bits are derived from the whatever the PC plus 4 is there. So from the PC plus 4, the most significant 4 bits will be concatenated with these 28 bits and all. So that is what here the process was mentioned. And in case of jump instruction, there is no any here if you look at here jump instruction, it just requires, there is nothing, it doesn't need any of the register operands, and it doesn't need the ALU, doesn't need data memory and so on. So therefore the circuitry, the data path changes that are need to be incorporate this particular jump instruction is very simpler. You can see here. So this is your whole data path as I have mentioned here, and I need to perform the jump. Suppose the instruction is jump and all. So you need to perform a decoding, because unless if you don't see the opcode, you don't know whether it's a jump instruction or not. So therefore here this is instruction fetch, and then the instruction fetch, that instruction, the opcode will be given to the controller. And now what you have to do, the purpose of this jump instruction is nothing but the PC has to be loaded with the address specified by the jump. The address specified by jump. That means in case of a jump instruction, the PC should not be loaded with the PC plus 4. The PC should be loaded with the new address which is specified as a part of a jump instruction. So for that, what you need to do, so the control will be just to see that the PC plus 4 should not be loaded. In place of PC plus 4, the jump address has to be loaded and all. So for that, what is required here, but at the time of fetching itself, we know that already PC plus 4 will be generated. So from the PC plus 4, we convert the jump address, we'll derive the jump address as the process mentioned. Whatever the 26 bits are there, that will be converted to 28 bits by multiplying by 4. It's nothing but shifting left by 2 locations. We'll get 28 bits, and these 28 bits are concatenated with this one, the PC plus 4, most 4 bits of PC plus 4 at the most significant side. So that way the jump address will be there. And now this jump address will be given as the input to the another multiplexer, because here there are two possible. Earlier so far without jump address, the address will be 2 possibilities, either PC plus 4 or branch address if it is a branch instruction, right? So this is the circuitry for feeding the PC, what will be the next address and all, right? And now we have one more possibility has come, that is a jump instruction. So in case of jump instruction, the PC has to be loaded with different from these 2 addresses. Different from these 2 addresses. It's not neither PC plus 4 nor this one, the branch address and all. So therefore, the jump address will be calculated by using this simple circuitry, just simply shifting and then concatenating the appropriately, so that a 32-bit jump address will be generated, right? And that is given as the input to that has to be fed now, right? So that is given as input. And then the previous circuit, whatever is there, and that is given as the input to the 0 and all. Likewise, we have 2 possibilities right now. Earlier, we have 2 possibilities already. Now we have the one more, the third possibility, right? Either PC plus 4 or branch target or the jump address. So to accommodate that, what we are doing is that for the previous circuitry itself, we are adding one more multiplexer to add another path, to add another address, the jump address and all. And now this multiplexer where again, the 2 possibilities are there, the earlier one and the new one, the jump address and all. And here this multiplexer will be controlled by this control line jump. There is a control line known to be jump and all. That means, so now the controller, in addition to the previous 10 inputs, so now if you want to design means now it has to, now the new controller has to be taken care of generating one more control signal also, that is a jump. So this jump will be active only in case of jump. By just noting this from the opcode, it will come to know that this jump address at that time. Actually, this line will be high. The jump line, we have to give signal here high, so that here if the signal is high, that means it will pick up the 1. That means whatever the input that is given to the 1 will be picked up, right? And otherwise it will be 0. And for all other instructions except other than jump, So this will be 0. That means whatever this multiplexer will be, like the one will this will be 0. So therefore the 0 will be picked up. 0 is nothing but from the previous one, whether it is a branch or PC plus 4. So that way you can add the jump instructions with a little modifications over the previous data path and controller and all. Here that means the controller has to generate one more control signal to handle this one. And then the jump means for preparing the jump address and all, we need to have some small additional hardware is required just to make to prepare the jump address of 32 bits and all. So that way, this is just an illustration or example to illustrate how the incrementally the processor can be enhanced. The processor can be like enlarged to accommodate the like all the instructions of the instruction set one after another and all. This is just an example where earlier so far there are 8 or 9 instructions are executed or can be implemented by using by using the previous data path and controller. And now if you want to add jump instruction to this one. So now how to do that, right? So this is just adding this and control line. So with that, the jump instruction can be smoothly added to the existing data path, right? Okay. So now, yeah, right. So with this, the current implementation, with this, there are certain issues. Like for example, if you look at here, for all the instructions, we are using the same data path. The same data path is used for all the instructions, whether it is like a load instruction or a branch instruction or whatever and all. Like the same data path and same controller are used for for all the instructions and all. So with that, what happens here is that, for example, in case of a jump instruction, if we see that the activity is very small, that means you need to just fetch the instruction, prepare the address, and then feed that PC. There is nothing else to do. But whereas in case of load instruction, you see that what is the activity and all. So we had to fetch, then afterwards you need to decode, and then here the register operands has to be fetched. ALU operation has to be performed, data fetched from the data memory has to be activated, and then again writing to the register file. So there are several activities that takes place in case of load instruction. I'm just saying. Whereas in case of jump instruction, the activity is very less. The activity is very less, just fetching and preparing the jump address and then feeding back, and then the next instruction will be fetched up. So likewise, when you're checking the various instructions, and some instructions require very less amount of time to perform its execution, whereas other instructions and some other instruction which requires a large amount of time to perform its execution and all. But here in this arrangement or in this simple design, so when you use this particular data path or controller in this manner, so we had to design the clock. That means everything has to be carried out in one clock cycle and all, whether it may be a jump instruction or it may be in a load instruction or some other arithmetic instruction and all. But as we are seeing that there is a variation in the implementation time. Strictly speaking, the jump may be performed in, for example, in terms of, for example, it may perform in, for example, 2 units of time, assuming that, like fetching is 1 unit and then this may be another unit. Whereas the load instruction, if you check it out, it has to pass through all these stages. That means all the data path components has to be carried out some task and all. So to perform all these tasks and also it requires more time. That means the load may require it requires more time compared to the jump instruction. So likewise, the other instructions also will take different amounts of time for performing its operation and all, right? And so therefore, to implement these instructions by using this data path and all, for that, what is required is that actually where the critical path, that means that the various components